Diamond is carbon arranged with strict sp3 hybridization. Each atom reshapes 1 2s and 3 2p orbitals into 4 identical hybrids pointing toward the corners of a tetrahedron at about 109.5 degrees. Every hybrid overlaps with a neighbor to form a localized sigma bond. Repeated through space, these bonds create a continuous three-dimensional framework where each carbon links to 4 others with equal strength and fixed geometry. The entire crystal behaves as a single covalent structure. Mechanical behavior follows directly from this pattern. The lattice has no easy slip planes. Deformation demands breaking sigma bonds rather than sliding layers. Because each bond is directional and equally strong, stress distributes uniformly. Diamond therefore exhibits extreme hardness and high elastic modulus. Yet this rigidity also limits flexibility. Once a crack begins, it can propagate cleanly along crystallographic directions. The same geometric precision that grants strength also defines its brittleness. Optical properties arise from electron confinement. Diamond has a wide band gap, about 5.5 electron volts, so visible photons lack energy to excite electrons across it. The result is optical transparency through the visible range. However, the dense field of localized bonds strongly polarizes light, producing a high refractive index and intense dispersion. The familiar spectral flashes come from this interaction of geometry and light, color born from refraction, not from impurity or coating. Thermal transport reflects the same perfection. Strong, uniform bonds allow lattice vibrations, phonons, to travel long distances without scattering. Diamond conducts heat better than any metal, while remaining an electrical insulator. The electrons cannot move, only vibrations carry energy. This coexistence of high thermal and low electrical conductivity arises naturally from sp3 bonding. Charge is localized, but motion of the lattice is free to transmit heat with remarkable efficiency. Although stable in appearance, diamond is not the lowest energy form of carbon. Graphite is thermodynamically favored at ambient pressure, yet converting diamond requires breaking and rearranging the entire sp3 network. The barrier is immense, so the transformation proceeds only under heat, pressure, or catalysis. Diamond endures because its structure resists reorganization, a kinetic stability born of tetrahedral connectivity. Its persistence on Earth is a record of bonds frozen far from equilibrium. Defects reveal the same structural logic. Substituting nitrogen introduces levels that absorb blue, giving yellow hues. Boron introduces acceptor states, creating blue coloration. Vacancies and lattice strains scatter light to yield brown or opaque crystals. Yet beneath all variations remains the tetrahedral network of localized sigma bonds, the source of diamond's hardness, transparency, insulation, and exceptional thermal conductance.